Okay, so last class we saw, we understood social networks, and we saw uh, a different technique for a measure betweenness, which would help us in hierarchical clustering on social network graphs. Now, in this class, we'll learn a few more things. The first one is triangles. So, uh, what are triangles in a graph? Essentially, three nodes, all of which are connected to each other, right? So, because of the locality property that we have been talking about, that if one node is connected to two other nodes, then those other nodes also are likely to be connected and likely to form the triangle or complete the triangle, right? So that's why the number of triangles in a social network graph is expected to be much larger than a random graph with the same size, like a same number of edges and nodes. And that means if we can count the number of triangles given the size of the graph, if we can count the number of triangles, it should give us some insights about the network. What kind of insights? That first of all, how much the graph looks like a social network. Secondly, age of a community. So what happens is a new community is formed. Okay, suppose you form a group in a social network or something like that. You add a few of your friends and things like that, and then other like-minded people join in and things like that. So something like this. uh, yeah, so let's say new community is formed, and these are the existing edges, and then afterwards some of these members will also bring in other like-minded friends, or people who will join in, looking at this and things like that. So suppose other members join. Okay, and then so suppose in this case, just a friend of D, C is a friend of D, so C joins, and then eventually such new members are expected to connect with other members directly like this. Okay, and even the already existing members, so essentially this community eventually they're likely to get to know each other, and they're likely to join, become friends with everyone, almost like that. So all the community is likely to become more and more dense age wise, right? So this means that the number of triangles or density of triangles in a social network gives you, I mean, can be very useful, and it gives you an idea about how mature a community is. Is this community or is this community kind of mm, uh, already matured, that they're functional, and so on. I mean, this can be one way of doing it. uh, by the way, in the next class, we will see how we discover communities. I have postponed it just because I just wanted to ask you, have you done spectral methods in graph algorithms course, or in algorithms course as such? Any, but maybe not all of you are taking such courses. So there's a spectral methods are actually pretty useful in certain graph algorithms. So next class we will actually take that up, and we'll see ways to discover communities, some methods of discovering communities and things like that. But anyway, so as of now, what we want to do is we want to count the number of triangles given a graph. So triangle counting algorithm. So let's say we have a graph VE where number of nodes is n and number of edges is m. So first, what we do is we compute the degree of every node. Okay, so we compute the degree of every node. That means we examine each edge. For each edge, we simply increment the degree of two nodes. So, and this takes order m time, right? Because that's a step one, pre-computation. Step two, we create a hash table. Okay, vi vj hash to 1 for every edge vi vj. That means it's just a dictionary kind of a thing. But I want to check whether this edge exists or not. Okay, so that given two nodes, we can determine if they have an edge between them or not. Okay, so this construction also takes order m time because you go through the edges. Okay, and for every edge you basically create a and create an entry in the hash table. And after this, each query is expected to take order one time, constant time with a proper hash function. So essentially, we have spent order m time, and later on, what we will do is we can check whether this edge exists given two vertices or given two nodes, whether this edge exists in constant time. Step 3, we create an index that from every node V to a list of adjacent nodes. Well, so this is just an index. Remember our MapReduce file index, right? So block to files or things like that. So similar to that, this is basically adjacency list. Okay, so adjacency list, we create that into, I mean, we form an index with that, so that given a vertex or node V, we can quickly get to the list. Again, the construction here would take order m time, and querying would take order 1 time. Querying means given an index, given a node V, to get to the list, it will take order 1 time. All right. So these are the pre-computation part, pre-processing part for our algorithm. Now next, first what we will do is we'll count what we call the heavy hitter triangles. What are heavy hitter triangles? To know that, we first have to know what are heavy hitter nodes. Since there are m edges, a node will be called a heavy hitter node if the node has degree greater than or equal to root over m. So total number of edges is m. If a particular node has so high degree that it is more than square root of m, then we call that node heavy hitter. That means the node is a very high degree, basically a quantified definition, this one. Now note that there can be at most 2 times square root of m heavy hitter nodes. Why? Because if there are more than 2 square root of m heavy hitter nodes, then our formula of the number of basically the total degree, right? So total degree, um, if there are so for every such nodes, our each such heavy hitter node has degree at least square root of m, and if there are more than these many, then the sum of the degree of heavy hitter nodes is going to be greater than 2m. But we know that our number of edges is m, so our total sum of the degrees cannot be more than 2m, right? Total sum of the degree is 2m. So that then we know that the number of heavy hitter nodes is at most 2 power m, 2 square root of m. So heavy hitter triangle is a triangle with all 3 heavy hitter nodes. So a triangle is called a heavy hitter triangle if all 3 nodes of the triangle are heavy hitter. That means their degree is at least root m. How many possible such triangles are there? Since there are at most 2 root m heavy hitter nodes, the number of possible heavy hitter triangles is 2 root m choose 3, and that is essentially order of m to the power half cube, right? So that is m to the power 3 by 2. So what we do is for each possible heavy hitter triangle, we use the hash table to check if all the 3 edges exist. Just a point here. Since we know the degree of all the nodes to start with, we know which of the nodes are heavy hitter nodes. So then for each of them, whatever the number will be less than equal to 2 root m, the number of such nodes. So for each of them, we can actually just explicitly check whether all of the 3 edges exist. That means after this, we'll be done with checking how many heavy hitter triangles are there. So this whole thing will take us order m to the power 3 by 2 time. Clear? It's basically just the complexity analysis is interesting. Otherwise, it is brute force, do everything kind of an algorithm. Okay. Now, so that's just counting heavy hitter triangles. Next is, what if there are, of course, there are triangles which are not heavy hitter triangles, right? That means nodes, triangles involving nodes, not all of which are heavy hitter nodes. So how to do that? So for that, we'll consider an ordering of the nodes Vi uh, or precedes Vj. Okay.
Sorry to interrupt. Just
Sure,
one
sure.
small question. What do we get by counting the number of triangles in this case? I mean, what is the significance of doing this?
Okay, so basically what we just described in the previous slide here. Uh, so the whole algorithms, the idea is count the number of triangles in a graph. Now for a social network graph, counting the number of triangles tells us how mature the network is as a social network, or given communities. I mean, social network will be, there will be several communities, right? You can actually also try that on a particular subset of the subgraph, essentially subset of the nodes and all their edges. So how mature the community is, essentially that's the idea. So counting the number of triangle has these two significance. Okay.
Okay, sir, thank you.
Okay, so now, so we have counted the heavy hitter triangles, other triangles. So consider an ordering of the nodes where Vi precedes Vj. This is the ordering. If first order by degree, if degree of Vi is less than Vj, then we write Vi precedes Vj. If the degrees are small, then the nodes had some kind of an ordering or index, right? ID. So then I should be less than j. So first order by degree. If degrees are tied, then order by the ID of the node. So that will be our ordering. Okay, we'll do the ordering because we want to avoid duplicate counting. We'll see in a moment. So now for each edge Vi, Vj, so for all edges, if both nodes are heavy hitters, then we skip because we have already considered those. Okay, so we have already considered heavy hitter triangles. So we have to only consider the cases where at least one of the nodes are not heavy hitters. So suppose Vi is not a heavy hitter. Okay, so suppose Vi is not a heavy hitter. Obviously, Vi is not a heavy hitter. Sorry, if Vj is not a heavy hitter, then Vi cannot be heavy hitter because the degree is even smaller. So let's assume Vi is not a heavy hitter. Then we'll use our index, adjacency list index for Vi, okay, to find the nodes adjacent to Vi. So W1 to Wk will be our adjacent nodes adjacent to Vi. To do, I mean, to access the list, it takes order one time, but then enumerating the list or reading the list takes order k time. Now, for each of these WLs, for L equal to 1 to k, we check whether, so these Vi and W1, Vi, W2, they are already edges. So we need to check whether they are also edges with Vj. So we need to check whether Vj WL exists. And that we can check in order one time for each of these, but there are k of them. So it will take order k time to check whether they are also edges connected to Vj. And obviously, only if Vi, Vj, WL are connected, then we count the triangle. But not only then, we count the triangle if and only if that edge also exists, and also Vi is less than Wn in our ordering of the nodes. This is to avoid the double counting. Okay, so then total time again for this will be order k, but order k, and we do this m times, right? We do this for each edge. There are m edges. How much is k? What is the maximum value for k? Anybody?
less than root m.
Less than root m, because these are, Vi is not a heavy hitter node. So let's say order root m. So we do this order root m times. So we do this order root m thing m times. So again, for total time for each edge will be order root m, and then for m edges total time will be order m times root m, that is m to the power 3 by 2. So to count heavy hitter triangles, it took us m to the power order m to the power 3 by 2. Also to count non-heavy hitter triangles, it took us order m to the power 3 by 2. So it's totally order m to the power 3 by 2. Okay.
Hello,
The
sir.
yes,
Yeah. So, sir, but counting only the heavy hitters triangle means that how the celebrities are, how the three celebrities are connected to each other, right?
I mean kind of you can think of, yes.
Uh, but we are interested in the general setup in the
That's
network.
what we are doing here, right? So the previous slide we showed how to count the heavy hitter triangles, and in this one we did how to count other triangles, right? So essentially a triangle is either a heavy hitter triangle or a not a heavy hitter triangle. So you take two cases. One case you do it in one way, another case you do in this way. Okay, so now the point is the algorithm looked pretty simple and straightforward. Just the complexity analysis was careful, but turns out that this is the best you can do. Okay, so how? So suppose G is a complete graph, then the number of triangles is actually m choose 3, right? You total all possible triangles are there, and that is order m to the power 3 by 2. So if the number of triangles is order m to the power 3 by 2, you cannot do better than that, right? Even you have to count all your triangles, so you have to actually do this. So you cannot even enumerate all triangles in less than that. So lower bound is order m to the power 3 by 2. Now obviously complete graph is not what we'll get generally. So obviously the worst case for any graph is order m to the power 3 by 2. But what if the graph is sparse? Okay, what if the graph is sparse? So let's say the graph is known to be sparse. By sparse we mean the edge to number of vertex, number of edges to number of vertex, m by n is much smaller, right? So as m by n is basically the ratio, right? So if G is sparse, we can show that even then the worst case complexity is order m to the power 3 by 2. Okay. Now this is a bit of a worst case complexity kind of a scenario. You may actually say at the end that, well, it doesn't look like a social network graph. Yeah, that's true, but the algorithmic complexity will still be, even for sparse graphs, the worst case complexity will still be order m to the power 3 by 2. How? So suppose you consider a complete graph G prime with n nodes and m edges. So this is a complete graph with n nodes, okay, with m edges, and note that m is then n choose 2, that is order n square. Now construct G from G prime by adding a chain of length n square. So something like this, you add a chain. Now I haven't maybe done n square here, but you add a long chain like this. Now what happens? You add a chain of length n square. That means you increased the number of nodes by n square, or n square minus 1 or whatever. So order n square. So you increase the number of nodes by order n square, but you increase the number of edges also by order n square. Okay. So the number of triangles will still remain the same because a chain does not increase the number of triangles. Okay. So it is still order m to the power 3 by 2. However, the number of edges will still remain the same order because the number of edges was already order n square. So it will still be order n square. But G is now quite sparse because your number of edges is order n square, but number of vertices is also order n square, right? So, so basically, G is quite sparse. I mean, the number of edges per vertex is like a constant factor or whatever like that. So that is very sparse. So theoretically, even for sparse graphs, uh, even then your number of triangles is order m to the power 3 by 2, which means your algorithm cannot do better than order m to the power 3 by 2. Well, now this of course doesn't look like a social network graph. In practice, obviously, what happens is in practice, well, I mean, given a real social network graph, one does not think about the computational complexity. Rather, what one thinks about is, well, it's a big one. How can we do it in parallel? So people actually do this by using multi-way join in MapReduce. Well, so I'm not going into that thing in the class, but it's pretty easily explained in the book. You can actually read it up. It's pretty straightforward from whatever we have done before in joins as well, right? So in practice for the actual computation, well, you have to actually check whether these edges exist, kind of thing, right? So that people use by joining the same copy of edge. So like E, then the set of edges, you join it with itself and again with itself, right? So that you implement using MapReduce, and you can actually implement that in practice for social network graphs. All right, so this is basically what I wanted to cover on counting the number of triangles. And as I said, counting number of triangles, so triangle is basically a 3-click. So counting larger clicks also are interesting problems people have looked at. So in uh, social network mm, data analysis, or people also call it computational social science. Why? Because they discover how people are connected to each other, and so on. Um, Discovering the number of different kinds of complete subgraphs is pretty interesting, or other kinds of graphs also, like a star. So how many stars exist? Star is like a 5-way or 6-way graph, but they're not. That's not a complete graph, right? So you know what a star is. So there are papers where people found that. I'll tell you the insight, social insight obtained from such papers. Um, so essentially, in a collaboration network, academic collaboration network, it has been such graphs exist. What kind of graphs exist? So suppose there are mm, it's funny, okay? So there are professors with extremely high degree. That means they have extreme high collaboration. Uh, so they have a lot of collaborators. Many of them are students, right? And a lot of those students also collaborated with other professors, but these two professors don't collaborate. Okay, so there are, such insights are also found in academic collaboration network, or co-author network and things like that. So there are funny things. Now you can ask whether it does make sense to do this kind of work or not, but well, yeah, social network are about insights, sometimes also about advertising and things like that, which bring a lot of money. Okay, mm, so next we will actually cover, yeah, so next we'll actually cover a few easy to understand intuitive concepts on social networks. They are also, these will actually seem like very easy and you already understand a lot of them, but just mathematical uh, definitions of such things quickly. So far we have been mostly thinking about undirected graphs in the light that we thought our networks could be symmetric. If A is related to B, then B is related to A, kind of a thing. Now, social networks also can be directed. That means set of nodes V and the directed edges. Sometimes directed edges are also called arcs. The web is one such network. Pages link to other pages. By the way, PageRank can also be used on social network graphs for various purposes, as you can imagine already. Uh, uh, so persons making calls to other persons, that can also be a directed net graph. Twitter, Instagram, people follow other people, that those are also directed graphs, primarily directed, and so on. Now, also all undirected graphs can also be considered as directed. You simply add both edges, right? So think of each edge as a bidirectional edge. So the following concepts, which are useful for directed graphs, can be used for social networks in general. So how? Paths and neighborhoods. Paths. So path of length k is simply a sequence of nodes v0, v1, dot 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 vk from v0 to vk, so that vi to vi plus 1 is an edge. Okay, directed edge. Simple. When path, essentially just you can go from this node to that node. That's a path of length k. Given the definition of path, we can actually define neighborhood. Neighborhood from a vertex or a node of radius d is set of all nodes such that there is a path from V to W of length at most d. So that means neighborhood of 1 means from V all the nodes you can reach. Neighborhood of 2 means from V all the nodes you can reach with 2 hops and so on. Now, just like you can define neighborhood of one node, you can define a neighborhood of a set of nodes also. Just if you are given a set of nodes, then the neighborhood of those that set of node V of length or radius d is all nodes which you can reach from this set of nodes within d hops. It's just a generalization of neighborhood. And the neighborhood profile of a node V is a sequence of sizes of its neighborhood of radius d equal to 1, 2, and so on. In other words, this is neighborhood of radius 0 will be obviously the node itself, right? Where can I go with 0 hops? I cannot go anywhere else. I'm here only. Okay, at V. Where can I go at with hop 1? All the nodes, that is essentially the degree. So the size of the neighborhood of radius 1. So that is essentially the out degree of V. The out degree of V, that means in one hop, where all can I go? Plus 1, that means the V itself, right? So 1 plus out degree of V. Similarly, neighborhood, the second one is the number of nodes you can reach with 2 hops and so on. And this sequence is called the neighborhood profile of a node. Okay, so why is this useful? Let's look at this example. So let's say, what is the neighborhood profile of the node B? So NB1 equal to 4. Why? In one hop, you can go 1, 2, 3, and B itself, right? So you can go to 4 nodes in the first hop. What would be NB2? Anyone?
6.
5.
6?
5.
Why 5? Why 6? So B2 means in 2 hops, where all can you go? So obviously all these 3 you can go, but in one hop you can go to D. That means in another hop you can go to everything. They're all directed, bidirected edges, right? I forgot to put the directions here. But anyway, so I mean you can essentially go anywhere, right? So neighborhood NB2 will be actually 7. Got it? So then you see that after that I cannot do anything more. So it's actually a finite sequence. So eventually, if the graph is connected, or even if it is not connected, you get stuck somewhere. After that, you cannot reach anything. So neighborhood profile is a sequence, okay? A finite sequence where the final number is likely to be all that you can reach. If it's a strongly connected graph, then the final number is the number of vertices. What about neighborhood profile of A? Okay, so NB1 is 3, right? A itself and B and C. What is NB2? NB2 is 4, right? So these 3 plus just a B. And then NB3, sorry, NA2 is 4 and NA3 will be 7. Now, you see the neighborhood profile of B and A are a bit different. This is the sequence 4, 7, and this is the sequence 3, 4, 7. So whenever the neighborhood profile has a very small jump, in this case the jump is only 1. In some cases it can have a jump of a slightly larger number, but a small jump. That means you are jumping across communities, right? So the neighborhood profile tells you whether a node is at the boundary of a community or at the center of a community, first of all, right? So whether if it's at the boundary, well, it can also be at the center as well as in the boundary. Maybe somebody knows everybody in the community, okay, and also many other people outside the community. So then it's also at the boundary as well as in the center. But essentially, Neighborhood profile gives you the idea whether some node is at the center or at the boundary or both. And then the profile tells you how many hops. Basically, this small jump tells you that you are actually going through a bridge like this. Now, uh, this also there are other concepts also come with this diameter. So diameter of a graph is the smallest integer such that for any two nodes there is a path of length at most d from v to w. I mean, this you have already understood, right? So diameter of a network is like that. So any two nodes v and w, what is the largest there's a path at most d. So that means if a diameter is 4, that means there are some nodes which are 4 distance apart. It only makes sense for strongly connected graphs or components, of course. I mean, if things are disconnected, then you cannot, the diameter becomes infinity. The web graph is not strongly connected, but there are large strongly connected components, and for those you can actually apply this. And there is this funny Kevin Bacon 6 degrees of separation conjecture, or it's actually popularly talked about anywhere in the world, that, well, the diameter of the graph of the people in the world is 6, not Facebook. Okay, Facebook, I mean, I may be, there may be people who are not on Facebook or some social network, right? But what it means is that uh, if you simply, if you consider the real graph of people in the world, I know you, you know somebody else, and so on. Okay, then from any person to any person, uh, the maximum distance is 6. Okay, that is the idea. Now that may not be reflected in Facebook, or maybe even the Facebook, the graph may be smaller because there may be people may actually be connected where they don't know each other and all that. So let's not bother about that. But this is the conjecture in the real world. And neighborhood profile of a node V is NV1, NV2, dot, dot, dot. I mean, mod of NV1, mod of NV2. Ultimately becomes the size of the graph for some K. Okay. So essentially then K is the diameter with respect to the vertex V, right? So K is the diameter with respect to the vertex V. That means from V, what is the largest distance to anybody? And the diameter of a graph, if the graph is complete, then of course dv is 1, everybody is connected to everybody. But normally, if the graph is connected, strongly connected but not complete, then the diameter of g is the maximum diameter of, with respect to any particular vertex. Okay, yeah. So yeah, so these are essentially the things about social network graph analysis. These are the measures people use. In the next class, we will probably take 1 or 2 more classes on this chapter. Next class, I will do spectral graph partitioning algorithms. I'll try to also do some hands-on on that. So yeah, so basically it will be about Laplacian matrix of graph and eigenvectors and eigenvalues of those and how they help us in identifying partitions. All right, any immediate question? Otherwise, we are done for the class. All right then. So thank you all. I will, as usual, post the materials on the website by this afternoon or evening, and then see
So
you.
this
Yes,
number,
go on,
this
go on,
number
go on.
6 seems pretty
Oh, sorry.
small for the.
Yeah, yeah. 6 seems pretty small, but it is. This is what it is. So 6 does seem pretty small, but uh, that's what they say. There is another uh, thing people use, especially the people who are intellectual people in the academic community, Erdos number, right? So that is diameter with respect to the vertex Erdos, Paul Erdos. Have you heard of Erdos number?
Yes,
Yes,
sir.
sir.
Yeah. So right. So that, if you see the definition here, that is the diameter. No, not diameter. Basically, the length of the path from you to Paul Erdos. So again, mm, similar concepts essentially. All right then. So see you on Tuesday, and yeah, and I'll post the materials this evening.
Sir, is it possible to have a doubt clearing session on Monday sometime? Because we have the submission for the assignment on
Oh
first.
yes, 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 yes. Just a moment, just a moment. So yeah.